Hi, Phil here. I'm going to go through you today with how we might use calculus in the classroom with our Maths-E kiddies. Going to be a little bit different, so I've got a couple of demos today. So if it works out, it works out. If it doesn't, oh well, doesn't matter. So first of all, when we starting, I think with anything, I think first of all we're going to start with easy problems. So what I've got here is a plastic cube. And if I fill that at a constant rate, at what rate is the depth changing? And so, yeah, talk about that now while I get ready. So here we go. So if I was to fill this up, and I'm trying to get it now so we can all see it, fill it up at a constant rate. So the water's coming out of there at the same speed. Some of the things that we might notice, and you might have some of these things in your school. Well, one thing that the kiddies should notice is while that's happening, the depth is increasing at the same rate. Well, how do we prove that? And that's what we're going to use a little bit of calculus for today. Excuse me while I put that down. So what we want to find here in terms of calculus is we want to find dH to t. That's the change in which the depth is varying with respect to time. So what do we know? I'm just going to move out the way for a seckie there. There we go, move that way. That we know that I'm just going to say, for example, that we're filling it up at 20 cubic centimetres or 20 mils per second. We know that the volume of water that's going into this thing here is 10 centimetres by 10 centimetres by that h, that depth. Should have used d, but I think h is better because it confuses the kids with d. And we notice that the dimensions on the sides don't change. So it's a lot of noting and noticing that we want the kids to be able to do. So if we look at this problem now and we use related rates, we want to find out what dH to t is. And so what we can do is we can use related rates and say dH to t is equal to dH to v times dv to t. One of the things the kiddies want to do here is they say, oh, can you cancel out the dv's? Well, which is okay if you cancel out the two legs of pi and say that's equal to tilde. That's up to you if you want to teach it that way. But dH to v, where have I got that 100th from? Oh, that's right. Yes. I'll just go back to dv to h is equal to 100. If I find the derivative of the volume with respect to the height, dv to h. dH to v then is the reciprocal of that 1 over 100 times 20 mils or 20 cubic centimetres per second. So the rate at which the constant rate at which the water is rising up the side of the tank there is 2 millimetres per second, and we've just proven the fact that it's constant. Well, how do we change that? I'm just going to empty the water out of that for a minute. And like I said, you've probably got some of these at school. I'd be surprised if you had them at home. So what I've got here is I'll just flick through all of that just then by touching the, there we go. I'm going to put that down so I don't click it. Here we go. We've got a square base pyramid, and that square base pyramid fits nicely into the cube. That's important. So what about if the cube was now a square base pyramid that fit into that cube? And I think the demonstration of that, I'll just click onto the next slide here while I do that. The demonstration of that is one thing that we'll notice is, if I can just get the right reflection, is that while I'm filling it up, it fills up quicker early on than it does as time passes by. And I think giving the kiddies, I'm just going to put that down before I spill it everywhere. I think that giving the students those toys to play with to make those what they notice, I think it's pretty important. I think it gives them that tangible, hands-on way of looking at it. And just because they're our Maths-E kids doesn't make them any less inquisitive. So what we notice is that the rate slows down as it fills up. We notice that the square on the top of on the water also changes as the pyramid fills. Different from the cube, where it was always a square. So it's a different type of problem, one that we'll talk about, where does it lead us to in a moment. So if we were to get ready, then we know that the volume of the square base pyramid is equal to 1/3 s squared h, but we know that s is equal to h. So missing there, you get 10 points for telling me that the volume is equal to 1/3 h cubed. And so once we know that, we can then find out what d vita h is. D vita h is h squared, and therefore we know that we're going to go for the reciprocal of that, to h to v is equal to 1 over h squared. So moving through the problem, we're going to get to h to t. What we want is the rate at which the height is changing, and the height is changing to h to v times to v to t. So can we cross out those to v's? Sure, same problem as before. I always tell kids that, you can probably mentally do that, but kids I don't really encourage it with the kids to actually physically do that. So to h to t is equal to 1 over h squared times 20, which is 20 over h squared, which the students might look at and say, what the heck does that mean? So if I was to look at that in a graph, there's y equals 10 over x squared. And I look at the relationship there, and I can see that the rate very quickly slows down as the more water's poured into it. And we can validate the result. I'm just going to go back a slide here. We can validate that h to t, the rate at which the height is changing with respect to time, is in fact an inverse squared relationship. And we can see by validation on the graph that as the depth changes, the rate at which the depth is changing decreases over time. So why would you do that? I think that it's good to think about sand mining when they're just over the conveyor belt and making sand castles. We can talk about how that's the dynamics of what's happening there. Filling dams, that's a bit of a topical point from time to time. And filling tanks and pools when we don't have when either we do have a constant cross-section or we don't have a constant cross-section. So just something to think about, just something for you guys to be wary of. Sometimes we can use these tools in the classroom. Like I said, you've probably got those things in your school already. So thanks for watching, guys. Catch you later.